current unit, we are studying two major functions, the exponential function, which we've looked at in the last two lessons, and now we're going to deal with its inverse called the logarithm, or logarithmic function. And key idea is this the inverse function of an exponential. All right, so first thing we're going to talk about is how to convert back and forth between logarithms and exponentials, then how to use that concept to evaluate logarithms, and then we'll go back to an old concept of finding the inverse function. It's 2.7 from earlier this year. So what is a logarithm? I know we studied them in Algebra 2, but a lot of times students after Algebra 2 really don't know what a logarithm represents. They're just so busy trying to understand the calculations. What a logarithm is, it's a function that finds the exponent. So a logarithm is equal to an exponent. So in other words, a log is an exponent. Okay. You could also think of it as the inverse of the exponential function. Normally you plug in the exponent and you know the answer. That's what we've been dealing with the last 2 days. So the logarithm is just going to say, hey, we know the answer. What did we plug in? That's going backwards, or the inverse function. So this page right here is the make it or break it page for this unit. We have to know how to convert between exponentials and logs. For an exponential form, you have something called the base, and you raise it to the exponent, and that equals some number. For short, I will now refer to this as Ben. Well, Ben has another form of his name. Ben, known to all his friends, is B-E-N, Ben, Big Ben. But when Ben goes home, he's not known as Big Ben. That's not the way his mom sees him. His mom sees him as her little boy, Benny. Ben-E, Benny. So it's just another way to rewrite Ben's name. And that's what the logarithm is. It's another way to rewrite a logarithm, an exponential function. So it's going to be the log of the base. So actually we say log base, and then we say the number of the number, and logarithms equal exponents. So the old form, the form we're used to, is Ben, and the other form's a little bit uncomfortable, Benny. Just like Ben would feel if his mom saw him around all his friends and started calling him Benny. All right, they are the same thing. They're equivalent equations. It's just a way to isolate a specific part of the exponential equation. So we're used to trying to get the number you get after doing the exponent by itself. Now we're going to give you that number, and you have to go find the exponent. Again, this is a make it or break it page. Anytime it ever says a definition, you should really pay attention to it, because that's what everything's based off of. So we are going to do our first couple of examples. We're just going to rewrite this in exponential form. So we want to put it in Ben form. So we have log base 6 of 36 equals 2, and that 2 is the exponent. So we write down our base, we raise our exponent, and that equals the number when we convert it. Now, when you have numbers here, it makes sense. 6 squared is 36, so you can kind of check it in your head. But the problem that you're going to get on your exam, on your test, you're not going to be able to do it in your head. It's going to be more like the second one. So we have our base. What are logarithms? Logarithms are, equal sign is, or form of the word is, are exponents. So we have u to the v equals that other number, 15/16. On your worksheet, you're going to have 4 problems like this, and then you're going to do another one where he makes you kind of work backwards, going from this form to logs. Then you're going to get 4 problems, I believe, that are like this. They're going to make you work backwards as well, and then they're going to give you problems where you have to actually go evaluate, find what the log is going to equal. So these are the other type of problems working backwards. So this time we're going to write it in log form. So log is the uncomfortable form. Log base of the number equals the exponent. So e form. So we have log. Our base is 64. Logs equal the exponents. So our exponent is 1/2. And the number is 8. Remember, 1/2 as an exponent is square root. So the square root of 64 is 8. Okay. So in this problem, we have our base, our exponent, our number. We're going to convert it to Benny form. So take your Ben form. Something you should be very well versed with: base, exponent, and then some other value, some number. And we're going to convert it to a logarithm. So log base u of v equals -14. All right. So now the last part of your worksheet is going to be about evaluating, simplifying expressions. This time we don't know the exponent. That is unknown. So what we're going to do to evaluate this, we're going to put something we're familiar with. We're going to raise our base to our exponent equals our number. So 4 raised to that exponent equals 64. So we're looking for that exponent. And if you know your powers pretty well, you know that is 4 cubed. If you don't want to write e, you can just call that x for our exponent. And then you can solve it like the very first worksheet that we did for this unit. That's what we're really doing, is we're just rewriting these problems so they're like the 4.1 worksheet. So if you don't remember how to do your exponents or don't have them memorized, you just divide, and I'll use the upside down division so we can factor it out. We use our base and we keep dividing by our base until we get our base. And then we count how many times we have that base. 1, 2, 3. So this becomes 4 cubed is 64. So we have 4 to the x equals 4 cubed. And then we'll still get x equals 3. All right, let's go to the next example. So I don't know what it's equal to. Let me call it x. We're going to raise our base to our exponent. Logs equal exponents. So the x is the exponent. And that is equal to 1 over 243. Well, I want this to become a power of a base of 3. To flip it, I need a negative. If you don't know your powers of 3 up to 243, then just keep dividing. So 3 goes into 24 8 times, so that's what? 240 divided by 3 is going to be 80 something. 3 divided by 3 is 1. 3 goes in here, what? 20 times. Carry the 2. 21 divided by 3 is 7. Divide by the 3 again. We get 9. Divide by the 3 again. Finally, we get 3. There's 1, 2, 3, 4, 5. So 1 over 247 is really 3 to the -5th. Means x is -5. All right, a couple of things we want to know. These are inverses of each other. What do inverses do when you compose them? They cancel out. I mean, think about it. You could just try to memorize that, or you can just use the same definition to get through this. Your base raised to your exponent equals your base raised to the exponent. So what does the logarithm equal? It equals this value here, which has to be x. Okay? So the log base b of b would cancel out, giving you this x. Same thing here. B raised to a power. That power is some power you would raise b to get x. So this whole thing's just got to be x. Okay? So they cancel each other out. So in your brain, when you see the base of the log, the base of the exponent the same, you just have this piece left over. If you have the base of the exponent first, and you get the base of the log, then it's just this number here. So let's look at a couple of problems. We got 12 to log base 12 of 144. Now the slow way would be, okay, let's evaluate the logarithm first. So this logarithm right here would be log base 12 of 144, which is 12 squared. Well, 12 to what power is 12 squared? That's 2. Then you have 12 squared, which is 144. If you learn the rule on the previous slide and remember that composition cancels of inverses cancel out, we go, oh, same base, gone. It's just 144. So why don't we use that concept here? We got log base 45, 45 raised to the 13th power, so it's just 13. If you don't know that, the way you would figure this out is you would take your base, the 45, equals, or raised to the x, equals this number, which is 45 to the 13th. Oh, x would have to be 13. I would like to be able to go straight there and get the answer on these problems with very little work. So no work needed on these two. Now, you cannot cancel these. The reason why you can't cancel these is because the base is not the same. So the only way you can cancel them is if the base is the same. And you can't cancel them if you try to put a number in front of a log, so be careful. So let's start off with trying to change this into a base of 3. So 9 is 3 squared. Well, what do I do now? Well, you do what you've always done when you've raised a power to a power. You multiply your powers. Okay. You want to cancel them out now, but you can't. It's not going to be 2 times 20. You have to do this. There's parentheses here. You have to deal with that before you can try to deal with this canceling. Well, the only thing I can think of is that multiplication is commutative. So how about I have log base 3 of 20 times 2? Thinking, how does that help? I just undo what I did here. So when you raise a power to a power, you multiply. Well, multiplication is commutative. So normally I go from this step right to here. I can switch the powers. As long as I'm dealing with real numbers, which we are in this problem, I can do whichever power I want to do first. So now I can see the 3 in log base 3 cancel, giving me 20 raised to the second power, which means the answer is 400. 20 times 20. The last 4 problems of your worksheet are like this. In fact, almost every example, not every example I've done so far, comes from that worksheet. So the worksheet should not take very long to do at all. There's some problems like these in the bookwork as well that you're going to have to do tonight. All right, let's move on to special logarithms. These logarithms are so special, we don't write their bases down. It's understood. The first base that we're going to talk about is base E. That is from our notes yesterday. So we are talking about log base E. Well, we don't write down log base E or log E. We write it as the natural log. Actually, it's the logarithm of Napier, famous mathematician, scientist who used logarithms in a lot of applications. So when we have this, this is just saying the base is E. The other one is the common log. And the reason why this is common log is because this is the one power people can do in their head that everybody seems to be able to handle is powers of 10. 10 to the 5th, easy. 1 followed by 5 zeros. 12 to the 5th, not so easy. So this one's common because we can commonly calculate it. This is known as log base 10. So common log because it's common and easy to do in your head. Natural log because that's the base of the natural function, exponential growth and decay, or the logarithm of Napier. So a couple more examples, things I would expect you to be able to do without a calculator. Normally I throw this on as a no calculator portion of a test. So we have the common log of, oh, let's see, hundreds, thousands, millions, billions, 1 trillion. So this is really a 10 here. So what I'm really thinking is 10 to what power equals this big number? That's easy. Powers of 10 are 1 followed by zeros. You just count the zeros. So this problem right here really is asking you to do log base 10 of 10 to the 3, 6, 9, 12th power. That cancels out and just gives you 12. We're not done. It then says add, so I'm going to add. And then I'm going to do this power. Remember, that power is 10. This is 1 followed by zeros. It's a power of 10. It's 1 over something, so we know it's a negative power. And then I count the zeros, 3, 6, 7. So this whole thing comes out to be 12 plus negative 7, and 12 minus 7 is just 5. All right, next example. 2 order of operations. We're going to do this multiplication last. So we have the natural log of e to the 20th. Wait, this is really saying 15 times log base e of e to the 20th. These cancel. So that gives us 15. That says times. That says times the answer, not raised to the answer. It clearly says times. So 15 times 20 is 300. Again, it's a problem you should be able to do without a calculator. All right. The last concept that we're going to talk about in our notes today is going to be the first concept we talk about tomorrow. We're going to talk about the inverse idea. And what we'll do after we get just used to finding inverses, then we will then do it for a very basic function and start graphing the inverse. Okay, so let's go back into the big concept, converting. So when you are trying to isolate something and you can't figure out how to get the exponent down and by itself, or you can't figure out how to get rid of a logarithm, when you get stuck on Ben, change it to Benny. When you get stuck at the Ben statement, change it to Ben. Other than that, we're going to just, when we have to isolate, you just follow the order of operations, do them backwards. The other thing about this, the old stuff from way back when in 2.7, the key concept for finding an inverse is every x becomes a y, every y becomes an x. It's got to be an equation. You have to change the variable and switch it to the other variable on both sides of the equation. The biggest mistake I see people doing when they find the inverse, they leave the left side of the equation completely off. That would, and they don't even write an equal sign down. That would be like going in English class and not using a subject or a verb. It makes absolutely no sense. So let's look at the last 2 examples. Find the inverse of each function. So to find the inverse, I'm going to take this y, this f of x, and I'm going to turn it into the other variable, because inverses, input and output switch. I'm going to turn this input x into the output y. Now, the next thing I'm going to do is I'm going to go isolate y. So I see that the first thing they do to y is times by 2. That'll be the last thing I do. I'll divide by 2. Then they subtract 7, so the last thing I would do, second to last thing I would do is add 7. Then they made it a power of 4. That's where we get a little bit stuck here. So that's when we get stuck with an exponential. We're stuck with a base raised to an exponent. I'm going to use a logarithm. Then they times by 3, so I divide by 3. The last thing they did was add 5, so the first thing I do is subtract 5. So subtract 5. Then divide by 3. You cannot divide to get this 4 gone. It doesn't say 4 times 2y to minus 7. It says 4 is a base raised to an exponent. It's going to give us some other number. Sometimes Ben gets a little weird, or he's trying to write a password for his computer, and he goes by an acronym of his name. He just changes things up, and now it's Nebby. All right? So it's okay. If you need to move and switch the sides of the equation so it looks like Ben for you, that's fine. When you're stuck on the exponential form, the Ben form, you're going to change it to the logarithmic form, the Benny form. So log base of the number And what do logarithms equal? Exponents. Now we can finish up. So I'm going to take this log base 4 of the quantity x minus 5 over 3. The parentheses are important. And I'm going to add 7. And then I'm going to divide the whole thing by 2. So put a half here and divide by 2 here, distribute. And that gives me my y. Well, once you find y, you found the inverse function. I know it's a function because exponential functions are one-to-one, so their inverses must be a function. So if they use f of x, I use f inverse. If they started with y, I end with y. All right, last example. Find the inverse function of g of x. So find g inverse of x. So I'm going to change y into x. Order of operations backwards. And I'm going to change, x into y. We're going to do our order of operations backwards. I'm going to take this minus 6 and add it over. Then I'm going to take this times 2 and divide it over. And then I'm stuck on this logarithm. So I need to know what the base is, and it's not written for me. Well, that's because this is the common logarithm, power that we can all do, powers of 10. So I'm going to rewrite it as base raised to my exponents. Well, what's my exponent? Logs equal exponents. So my exponent is x plus 6 over 2. Make sure I don't rewrite it and misread it as 10 times. It's 10 raised to it. And that equals 3 minus y. So what I'm going to do is I'm going to add this y over here, make it positive, and subtract this one over. Or if you'd rather, you can subtract 3 and divide by -1. That's the easy part, is isolating. All right, I'm just going to erase my y now that I have it by itself, and I'm going to go use inverse function notation. So it's the inverse of the g function, so g inverse of x. This will definitely be a problem I will put on the test. Okay, I'm going to go ahead and do one more. This is where we're going to start tomorrow. This is a quick and easy one. Find the equation of the inverse algebraically. Take this x and this y that we have and turn it into x. Isolate y. That's easy. We got a base, we got an exponent, we got a number. I want the y by itself, I want the exponent by itself. And what finds exponents? Logarithms. So we have log base 3 of x equals our exponent y. So f inverse of x equals log base 3 of x. In our next lesson, we will take the same problem. We will graph this. We'll talk about how we found the graph of the inverse from 2.7 and develop a parent function for logarithms. So the expectation is that you finish the worksheet and turn that into Schoology before tomorrow is over. And then tomorrow, you're going to watch the video on day 2. You can do all these problems from day 1. I expect you to do those today. And then tomorrow, we're going to add in these problems. And then the day after tomorrow, that's when you're going to turn in the entire assignment. It's just one big assignment for 4.3. All right. If you have any issues or questions, make sure you watch and rewatch as much as you can of the video that you need to. There's other things you can go look up, or you can always pay attention at our Zoom meetings, and I'll answer questions then.